So we will compute this integral over the boundary of B, the unit circle. We want to compute f1 f2x dx plus f1 f2y dy. Okay, our condition is that f1 xy square plus f2 xy square is 1. So how to compute this integral? Here is the B. This is the boundary of B. To compute this integral, of course, we take a parametrization of the boundary curve, the unit circle. So we take let x equal xt, y equal yt be parametrization of the boundary t inside interval alpha beta. Then for t in the interval, our xtyt is f xtyt. Because our map f satisfies this condition, it is identity map on the boundary. Okay, so if a point is on the boundary, the image of this point under our map f is still itself. Okay, so since xtyt is a point on the boundary, therefore fxtyt equal fxtyt equal xtyt. Now fxtyt is the component is f1 xtyt, f2 xtyt. Okay, so this means f1 xtyt is xt and f2 xtyt is yt. Now we applied the computation formula for the line integral. We see that using the parametrization, of the boundary, we see that I is the integral of alpha beta from alpha to beta f1. So the method to compute the line integral is to substituting the parametrization into the integral. X equal xt, y equal to yt. Dx is x prime dt, dy is y prime dt. Okay, so the f1 here should be replaced by f1 xt yt, and the f2 with respect to x, that is f2x, also substituting xt yt. Then dx is x prime dt. We take dt at the final step. Then plus here f1 f2y, we take the f1, the common term f1. We take the common term f1 outside everything. Therefore, we only need to write f2y. f2y is f2y xt yt. Then dy is y prime t. then dt. Okay, so what's this? This is precisely alpha beta f1 xtyt. Then the expression contained in the bracket is the derivative of f2 xtyt with respect to t. Using chain rule, you will see that the sum of the two terms inside the bracket of the last line is just the derivative of f2 xtyt with respect to t. Of course, we have dt here. But the f1 xtyt, what's f1 xtyt? As we mentioned, f1 xtyt is xt here. And the f2 xtyt is yt. So this equal alpha beta xt y prime t dt. This is the integral over the boundary curve of x dy. And as you know, because you already studied Green formula in calculus 2, I just know this. So as you know, this is pi. This is the area of the unit disk pi. So we conclude our computation of this integral in the proof of our proposition, this integral. The result is that it equals pi. So this integral equal to pi is a contradiction that if the map in the proposition exists, then this integral is 0. So our verification that this integral equal to pi is complete. This integral equal to pi complete. So this complete the proof of this proposition. Okay, so therefore we have the two-dimensional Brouwer fixed point theorem, and of course we also introduce you the n-dimensional Brouwer fixed point theorem. But we could not prove the n-dimensional Brouwer fixed point theorem here. Maybe we'll prove this later in the future. Maybe I have no plan. Now, having proved the Brouwer fixed point theorem, we will introduce an interesting application. Example, application of Brouwer fixed point theorem. Let A be a n by n matrix, invertible, and G is the continuous map from Rn to Rn. Moreover, G satisfies this condition. What this means? This means G is grows not so fast. The numerator Gx is a vector valued function. Of course, you can also take the norm, but this is equivalent. It is no matter whether you take the norm or not on the numerator, but you could not remove the norm of x at the in the denominator. Okay. So this means that Gx grows not so fast. Gx grows slower than the norm of x. So the limit is 0, meaning that Gx is growing not so fast. It grows slower than the norm of x. Then the result is that there is some point B in some point C in Rn. such that xc equals gxc. Okay? In other words, the nonlinear system of algebraic equation ax equals gx has a solution, solvable. Okay? So this is a very interesting result. It is the generalization of what we know from linear algebra. A particular case, gx is a constant vector b. Gx is a constant vector b. Of course, a constant map is continuous. So continuous assumption verified. And also as a constant, the limit of course is 0. Because the numerator, the norm of the numerator is fixed, the norm of b. But the norm of the denominator increased to infinity. So the limit is 0. Therefore, for the special case that gx is b, our result is just that if a is invertible, then ax equal to b has a solution. This is just the conclusion of the Clymer law in linear algebra. Okay, so this result can be considered as a nonlinear generalization of the Clymer law in linear algebra. Okay, now we want to prove this result. Of course, we want to apply the Brouwer fixed-point theorem. Because the fixed-point theorem is very useful in solving the existence of solutions for equations, in particular nonlinear equations. So we need to construct a ball, and we prove the Brouwer fixed-point theorem. The Brouwer fixed-point theorem is about a map defined on the unit ball, but it is easy to see that the result can be transformed to a ball of arbitrary radius. A ball of radius r, the result is also true. So we need to find a radius r large enough, and also find a map so that we can apply the Brouwer fixed-point theorem for the map on the closed ball of radius r, so that the map, the fixed point of the map is the solution we want. So, and also we see that ax equals gx is equivalent, because a is invertible, to x equal a inverse gx. Therefore, to prove this result, we applied Brouwer to the map. The map is our f, defined on R. Fx is a inverse gx. Since g is continuous, and a inverse is also, as a linear map, is also continuous, so this map is continuous, no problem. This map is continuous, no problem. The only question is that if x belongs to B, can we have fx also belongs to the ball BR? This is the only problem we need to answer. If the answer is true, then we can apply the Brouwer fixed-point theorem to the map F and get the fixed point of F. And because of this equivalent, fixed point of F is solutions of our nonlinear equation ax equal to gx. Okay. So how about this question? X belongs to BR. Can we have fx belong to BR also? The answer is that if R is large enough, this is true. For small r, this might not be true. So we need to prove that we can find an R large enough so that this is true. Now we let R to be undeterminate. So we argued below. Let R to be determinant. To be determinant. Now, if the norm of x is not greater than R, let us consider the norm of fx. The norm of fx is the norm of the metric gx. Then by the definition of the norm of a metric, we know that this is not greater than the norm of the inverse metric multiplying the norm of gx. Okay, so how about the norm of gx? To analyze the norm of gx, we use our assumption that gx is slower than the norm of x. From this assumption, we see that for any epsilon positive, there exists a constant c positive such that gx will not greater than plus c. This is for any x in Rn. I left this as an exercise for you. This is a very easy exercise because the limit is 0. You can apply some no result about the continuous map we learned in the very beginning. So using this result, this result I will not prove here, exercise. Okay, using this result we can continue our estimate. So this will not greater than the norm of A inverse. Then the norm of gx will enlarge by epsilon x plus c. That is epsilon multiplying the norm of A inverse. Then the norm of x is not greater than R plus the norm of A inverse multiplying c. Okay, this is our estimate. Now the right hand side, no x appear on the right hand side. So we want the norm of fx. We want fx to be to lie in the ball of radius r. So if the right hand side is not greater than r, if the right hand side is not greater than r, we already proved that if the norm of x is not greater than r, then so is the norm of fx, and f is really a map from BR to itself, and our proof is complete. Okay, so can we have this final inequality? Can we have this? The answer is yes. Because for the epsilon is arbitrary. We take epsilon smaller than some number. We assume we take epsilon positive but smaller than the norm of the A inverse, then inverse again. Then epsilon A inverse less than 1. The coefficient of this inequality less than 1. So you can solve this inequality to see that if R is greater than some number, if R is greater than say A inverse norm, 1 minus epsilon A inverse. If R is so large, you can see that if R is so large, then the final inequality is true, and our proof is complete. Okay, we can choose R so large because the denominator is, because epsilon is small enough so that the denominator is positive. The denominator is not 0 or not even negative. It is actually positive. So we can solve this R, and this completes the proof. So that is, we take epsilon so small so that the final inequality is solvable, have the solution r greater than this number, then for r so large, our argument shows that if x lies on the ball of radius r, then fx also lies in the same ball. Therefore, f is a map from the ball to itself, and we apply the Brouwer 50-point theorem to obtain a 50 point of the map f. The 50 point is the solutions of our nonlinear systems of algebraic equation ax equal gx. Okay, so this is the application of Brouwer 50 point theorem.